In this video, we will discuss another application of mean value theorem. Right? Let's try to sketch the mean value theorem before we use it. So we are given a closed and bounded interval from A to B, right? Now we are given a function, right? The function here is continuous. So this is our function y equal to f of x, such that first f is continuous on a, b. Second, f is differentiable on a, b. Right? Before you apply any result, you have to check whether the assumptions are satisfied. If you get your assumptions, the assumptions are not satisfied, the conclusion you make will be wrong, right? You could make some very bad conclusions, right? So before we apply mean value theorem, we have to make sure our function is continuous on the closed interval from A to B, and also differentiable on this open interval from A to B, right? Then from here to here, A f of A to B f of B, you get a secant line, right? And so this is our point A f of A, and this is our point B f of B. So because this function is nice, being continuous on the whole interval, being differentiable on in the inside the interval, right? Then you can get another point. Another point. Let's use a black. And you can call it a C here, right? This is our C here, such that the tangent line to CF of C is parallel to the secant line we have, the blue line, right? Then there is a C inside AB such that these two lines are parallel, means slope to be same. Slope of the tangent line is f prime of C, and slope of secant line is f of B minus f of A over B minus A. So that's a beautiful connection between the function values and derivative, right? So let's see some applications. Just see one example where we can apply this to make some judgment, right? So suppose what? Suppose f of 0 equal to -3. F prime of x cannot be too big. This is less or equal to 5 for all x values, which means this function is always differentiable. Always differentiable means always continuous, right? So we want to know how large can f1 possibly be, right? So that's our question, a standard application of mean value theorem, right? You are given the information of the derivative, you are given one function value, you want to try to get some restriction on the second value, right? Because the derivative is not too big, so f1 cannot be arbitrarily big, right? Because otherwise you get some contradiction. So let's try to do this, right? Solution. Let's try to check our assumptions. As I said, if the assumptions are not satisfied, the conclusion you obtain will be wrong. In many cases, it will be wrong, right? So, and since Since what? Since f prime exists for all x value. We know that f here is continuous and differentiable. On right. Now we have to figure out which interval we want to apply mean value theorem on, right? So you want to control f of 1 using f of 0, right? So clearly the interval should be 0, 1, right? This function should for sure continuous on 0, 1 closed and open on 0, 1 open, right? Differentiable on the interval, open interval from 0 to 1, right? Now we are ready to apply mean value theorem because the assumptions are satisfied, and also we are aiming for control one function value based on the other, right? So mean value theorem will do the job, right? So applying the mean value theorem, there is a C inside 0, 1 such that f of 1 minus f of 0 over 1 minus 0 equal to f prime of C, right? We do know that f prime of C is always less or equal to 5, right? So we get, and so f of 1 minus f of 0 over 1 is less or equal to 5. So f of 1 should be less or equal to 5 plus f of 0. We do know f of 0 is negative 3. So f of 1 is less or equal to 2. So that's our final answer for this problem. So the largest possible value for f of 1 is 2. So that's a application of the mean value theorem.